This is going to be the final lecture for Chapter 19. We're going to cover sections 9 and 10, which are more about reading than they are actually working problems. The summary here is that nerve impulses in the body are basically an electrical process. Currents through the human body as small as zero point 0.1 amps can be fatal because they interfere with this process. It also occurs in heart and other muscle cells. House wiring, one line enters the house, it's considered neutral, or at least at the same voltage as the ground. The other one or two wires are considered to be hot. The maximum current available from an individual circuit is limited by the resistance of the wires. If they carry too much current, then the power loss, tabulated with this, is going to cause them to overheat. Protection against overloading the circuits is provided by fuses or circuit breakers. So if we take a look at the physiology of nerve cells, an axon, along with the electrical impulses, can travel, includes a cylindrical membrane with one conducting fluid inside and another outside. And then you have a potential difference here, usually around minus 70 millivolts, if you could actually measure that with a voltmeter. So you've got the positive ions out there, you've got the negative ones in here. So that's at rest. Then when a pulse propagates, the membrane depolarizes. Then you see the membrane potential go to positive 30 millivolts, and then the positive ions enter the cell. And then as that wave travels through, the membrane briefly hyperpolarizes, and the membrane goes to minus 90 millivolts. When that pulse is initiated, the nerve membrane temporarily becomes more permeable to the ions in the fluids, leading to the drop in potential. As it propagates, the membrane recovers and overshoots. So this is responsible for the body's great sensitivity to externally supplied electric currents. Impulses equivalent to those carried by nerve cells also occur in muscle cells, where it allows you to contract. Thus, muscles as well as nerves are sensitive to currents. As a result, electric current can cause three different kinds of damage to the body. They can interfere with the nervous system, they can interfere with convulsive muscle action, and they can also cause burns due to the heating. So we've already discussed that currents as small as 0.1 amps can be fatal because they interfere with nerve processes that are essential for vital functions, like your heartbeat. The resistance of the human body is highly variable. Body fluids are usually quite good conductors because of their substantial ion concentrations. But the resistance of skin is relatively high, ranging from 500 kiloohms to 1,000 ohms or so for wet skin, depending also on the area of contact. If your resistance is this and you get a current applied of that, then that requires a voltage of 100 volts. And that's within the range of household voltages, and is one reason it is dangerous to receive a shock with wet skin. But even smaller currents can be dangerous. So let's say you got 0.01 amps to the arm or leg, it can cause strong convulsive muscle action and considerable pain. Double that, a person who is holding the conductor that is inflicting the shock is typically unable to release it. And that's a real problem. Currents of this magnitude through the chest can cause ventricular fibrillation, a disorganized twitching of the heart muscles that pump very little blood. It just kind of sits there and flutters. Surprisingly, very large currents are somewhat less likely to cause fatal fibrillation because the heart muscle is clamped in one position. The heart actually stops beating and is more likely to resume normal heart beating when the current is removed. The electric defibrillators used for medical emergencies apply a large current pulse to stop the heart and give it a chance to restore normal rhythm. Under certain conditions, voltages as small as 10 volts can be dangerous, and all electric currents and equipment should always be approached with respect and caution. Now, if we look at practical household and automotive electric power distribution systems, automobiles are going to use DC systems, direct current, and we'll get into that later. And nearly all household, commercial, and industrial systems are going to use AC because of the ease of stepping voltage up and down with transformers, and we'll get to that later. Most of the same basic wiring concepts apply to both systems, and we'll talk about alternating current systems later on in Chapter 22. The various lamps, motors, and other appliances to be operated are always connected in parallel to the power source. The wires from the power company from the house to the battery and alternator for a car. So the basic idea of house wiring is shown here. One side of the line as pair of conductors is called the neutral side. It is always connected to the ground at the entrance panel. For houses, ground is actually an actual electrode driven into the earth and is sometimes connected to the household cold water pipes. And electricians speak of the hot side and the neutral side of the line. So you've got the hot side here, and then you've got the neutral side over here. You can see here, you've got a main fuse, you got another fuse here, and you got another fuse here. You got several outlets, a switch, light, whatever else. Household voltages nominally in the US and Canada, you're looking at 120 volts. It's about twice that in Europe. I think it may be twice that in Australia too. I'm not sure. I'd have to look that up. The power input, P, to a device is going to be given by equation 19.9. P is equal to voltage times the current. So for example, the current in a 100-watt light bulb is going to be, you got the power here, you've got the voltage here, that's the current. The resistance of this bulb at operating temperature is going to be V over I. So you can see that 144 ohms. Or R, V squared over P is 144 ohms as well. Similarly, a 1500-watt waffle iron draws a current of 12.5 amps and has a resistance of 9.6 ohms at its operating temperature. Because of the temperature dependency of resistivity, the resistances of each of these devices is considered less when they are cold. If you measure the resistance of a light bulb with an ohmmeter, or ohm meter, whose small current causes very little temperature rise, you'll probably get a value of about 10 ohms. When a light bulb is turned on, there's an initial surge of current as the filament heats up. That's why when a light bulb burns out, it nearly always happens just as you turn it on. The maximum current available from an individual circuit is limited by the resistance of the wires. The I squared R power loss in the wires causes them to be hot. In extreme cases, this can cause a fire or melt the wires. Ordinary lighting and outlet wiring in houses usually use 12-gauge wire. It's got a diameter listed here and carries a maximum current of 20 amps safely. Larger gauges are used for high current appliances, for example, ranges and clothes dryers, and 2-gauge or larger is used for the main power lines entering a house. Protection against overloading and overheating of circuits is provided by fuses or circuit breakers. So a fuse is going to contain a link of lead tin alloy with a very low melting temperature. The link melts and breaks the circuit when the current rate is exceeded, which is what you're looking to do because you don't want it overloaded. The circuit breaker is going to be an electromechanical device that performs the same function using an electromagnet or bimetallic strip to trip the breaker and interrupt the circuit when the current exceeds a specific value. Circuit breakers have the advantages that they can be reset. A blown fuse must be replaced, but those fuses are somewhat more reliable in operation than the circuit breakers can be. So you got a question and answer session over here. I thought this chapter was pretty interesting myself. I hope you got something out of it.